Continuing in chapter 3, section 4, now it's time to look at conjugates. I'm actually going to go back to the previous page to talk about conjugates. Back up here in example 5, we actually found some conjugates. These two solutions are what we call conjugates. What we see, if we can still see, is that conjugates are formed by taking and changing the subtraction to addition or addition to subtraction, meaning we keep the two numbers up front, -3, and the two numbers behind, square root of 5. We keep those the same, but we change from subtraction to addition or vice versa, addition to subtraction. So we found conjugate pairs of irrational zeros. And that's always going to happen when we come from using the quadratic formula, because we're going to have plus or minus with the irrational zeros. Likewise, look down here at the imaginary zeros. When we use the quadratic formula and we ended up with imaginary solutions, we ended up with a conjugate pair. Okay, these two zeros are conjugate imaginary zeros. Look at the 2 and the 2 are the same, and the 3 and the 3i and the 3i are the same terms, but one expression has a subtraction and one has addition. These are conjugate imaginary solutions. And all irrational and imaginary solutions, roots, x-intercepts, occur in what we call conjugate pairs. All right, so looking at conjugates a little more deeply, a conjugate is formed by changing the sign between two terms in a binomial expression. Changing the sign, meaning addition to subtraction or subtraction to addition. Conjugates always have special multiplication characteristics. Multiplying by a conjugate can simplify many expressions. All right, these are rational conjugates because you can see that the number 2 is rational, not irrational. Okay, x plus 2 and x minus 2 are what we call conjugates. Look what happens when we multiply conjugate pairs. So if I took a binomial times a binomial, I can FOIL. I'm going to get x squared up front. I'll get minus 2x. But right here, when we go to the inside terms, we're going to get plus 2x. These will cancel. Okay, and then I also have to do the last multiplication to get minus 4. So I can simplify this, and I can just get x squared minus 4. So if I knew that I'm multiplying by conjugates, I could avoid doing the whole foiling thing and just think about multiplying the numbers up front, or the expressions up front, x squared, and multiplying the last two terms and getting minus 4. All right, these are rational conjugates because of this number right here. 2 is rational. Irrational conjugates. Well, the 2 and 2 are rational numbers, but square root of 3 is going to be your irrational number. These are conjugates. Let's multiply them and see what happens. So foiling, I'm going to get 2 times 2 or 4 minus 2 times the square root of 3. And then here, plus 2 square root of 3. So these terms will actually cancel. And then right here, when I multiply the last two, I'm going to get minus the square root of 9. Minus the square root of 9, which is just 3. So really all I have is 4 minus 3, and this would even simplify further down to an answer of 1. Okay. A quick reminder too, remember when you're multiplying 2 times square root of 3, we can't multiply the 2 inside that 3. The 2 has to just be out front. But when you multiply two radicals together, square root of 3 times square root of 3, you can multiply the 3 and the 3 together and get the square root of 9, but that again did simplify to 3. All right, and the last type of conjugates are the imaginary, also called complex. So notice that 1 and 1 are rational numbers, but the 2i and the 2i are your imaginary terms. So these are conjugates. What happens when we multiply them? So 1 minus 2i, but right in here you're going to get the plus 2i. And then here we're going to get minus 4i squared. All right, these will cancel. So we're left with 1 minus 4i squared. Okay, we defined I to be the square root of -1 quite some time ago. So if I were to square both sides, I squared is actually equal to -1. So I could further simplify I squared. I could change I squared to a -1. And remember, you're multiplying into the 4, so that actually adjusts and makes this sign up here become a plus. So -4 times -1 is +4. So my final answer here would be 5. So multiplying conjugate pairs, you know, like it says, has some kind of special multiplication characteristics. So when you FOIL conjugate pairs, you really only have to do the first terms multiplied and the last terms multiplied, if you see that pattern. All right, continuing, let's look at irrational conjugate theorem and complex conjugate theorem. And I've already mentioned this. This is just words being put to what I mentioned earlier. If a polynomial equation has a root or x-intercept or 0 of a plus square root of b, then and a is a number and b is a number, then it also has the root a minus square root of b. Likewise, if a polynomial equation has a root or 0 of a plus bi, a is a number, b is a number, here's your imaginary, then it also has the root a minus bi. Irrational and imaginary roots occur in pairs. So, and that's what it says here. So if a function has these zeros, x equals 4 and x equals 1 plus square root of 5, what other 0 must it have? Must it have? Well, there was nothing that was ever said about rational zeros occurring in pairs. Just because I have 4 as a 0 doesn't mean -4 is. And just because I have -6 as a 0 possibly doesn't mean 6 is. But I do know that if 1 plus square root of 5 is an irrational 0, it also has to be that 1 minus square root of 5, its conjugate, is a 0. Let's look at this second example. Let's say a function has these zeros. X equals 3, that's a rational number, and x equals 3 minus I. What other 0 must it have? Well, I look for the irrational or imaginary zeros, and if both the conjugates aren't reported, then I have to go in and put the conjugate that's missing, 3 plus I. All right, and now our final objective. That information is all going to help us to write functions. So now everything that we've been doing in this lesson to find zeros, we're actually going to do the reverse. We're going to be given the zeros and asked what is the equation that these zeros came from. And now that we have all this other information, we can put it all together and accomplish that task. So we can use the above information and known zeros of a function to write a function in its simplest form. The directions are, let's find an nth degree polynomial function with real coefficients satisfying the given conditions. So this is what's given in example 1. We're told that n is 3. Well, that means we're dealing with a cubic polynomial. That's our degree. The highest degree is 3. That means that there are 3 zeros. Then it goes on further to say that 4 is a 0 and 2i is a 0. So I'm going, well, that's only 2 zeros. So remember, if x equals 4 is a 0, there's no guarantee that x equals -4 is a 0. But if 2i is a 0, then I know that its opposite, -2i, is a 0. So let's count them. We've got 1, 2, 3 zeros, and it should match the degree. This information right here is going to help us to finalize our answer. So we'll put that on hold for right now. So what do I do if I know the zeros, but I want to know the equation that it came from? Well, let's write the factors. So we did this in the previous lesson. So the function that these are zeros of comes from some number called a subscript n. And if I have 3 zeros, I'm going to build 3 factors. So x equals 4 comes from x minus 4. Think about subtracting a 4 to both sides of this equation and zeroing out this side. You're going to get x minus 4 as the factor that gives x equals 4. Think about subtracting 2i to both sides of this equation, and you're going to get x minus 2i. And this factor will be x plus 2i. Am I done? Well, let me go back to the question. Find an nth degree polynomial function with real coefficients. These are imaginary numbers. So what do we do next? Well, let's multiply these two conjugates together. So keep the f of x, bring it down, that's important. Bring down the a subscript n, and then bring down the x minus 4. Now let's focus our attention on multiplying these conjugate pairs. And remember what we saw earlier, they have special multiplying characteristics. So all I have to do is multiply the x and the x and get x squared, and multiply the negative 2i and the positive 2i. That's going to give me minus 4i squared. Well, remember, 4i squared, let's just kind of write it right here. I squared is negative 1. So I've got x squared minus 4i squared, but I squared is negative 1 to multiply into this negative 4 here. So actually this parenthesis will be x squared plus 4. And I'm kind of running out of room, so I'm going to put it right here. So I still have the a subscript n, I still have the x minus 4, but right here I have x squared plus 4. When you multiply negative 1 times the negative 4 here. Okay, we want to keep multiplying. So now that we multiplied the conjugate pairs first, now we have another binomial to multiply by this binomial. So let's FOIL on this because there is no special multiplying characteristics going on because these are not conjugates. So x times x squared is x cubed. Well, there's the cube that we need for the third degree, plus 4x minus 4x squared, and then minus 16. All right, I'll probably go ahead and rewrite it and put it in a better order. Remember, this is a parenthesis here. X cubed, and I put the 4x squared minus 4x squared next, and then plus 4x, and then minus 16. Okay, am I done? Well, let's go back and look at the question. Did we find an nth degree polynomial function? I did, third degree. Real coefficients. Yeah, I don't see any more imaginaries. I took care of that when multiplying. But I have this issue right here of a sub n. I need to know what number that is. Well, you've probably forgotten, but let's remind ourselves that there was some additional given information. Okay, this actually is a point that's on this function. So think of this as your x value and this is your y value. So what we're going to do is we're going to come down here. In order for us to find this value of a sub n, well, I'm going to plug in negative 1 for all these x's. And when I do that, I'm going to put 50 over here where y is, or f of x. So let's think about f of x is 50. A sub n, keep parentheses. Negative 1 cubed is negative 1. Negative 1 squared is positive 1 times negative 4. Negative 1 times 4 is minus 4. And then I have the minus 16. We'll go to our calculator and we'll get negative 25. So now I have a sub n times negative 25 equals 50. I can now, because I'll have all numbers, let's divide both sides by negative 25 and negative 25 over here. These will divide out into a 1, so that tells me that a sub n is actually equal to negative 2. Am I done? Almost. One last thing we have to do here. I have to go back and insert negative 2 back up here into this f of x equation. I'm just not sure where I'm going to put it. I guess right here. So the function f of x is equal to negative 2 times, and then I would bring down x cubed minus 4x squared, etc. And likely what we should do here as an answer is distribute that negative 2 inside to all the terms of this third degree polynomial. So negative 2x cubed plus 8x squared minus 8x plus 32. Are we done? Yes, finally. So let's take a look back. They gave us some zeros. They told us the degree. We had to decide if we were missing any zeros. We changed these zeros to factors. We chose to go the smart route of multiplying conjugates first to then multiply into the remaining binomial. We did the multiplication. Okay, we kept the a sub n all the way down. Where do we get a sub n from? Going back to this additional information where this is x and this is y, changing all your variables to numbers, and then doing the computations on your calculator, and then going back and inserting -2 for that number, and then finally distributing to get the third degree polynomial with real coefficients. Whew, if you run out of time on the test, this might be the one you sacrifice. All right, let's do one more example. And I think I'm going to do it on the back because it's already crowded. All right, so it tells me that I have a 4th degree polynomial, so my answer should have a high exponent of 4. It tells me that I have zeros of -2 and 2, and then also I is a 0. And it told me that f of 3 is -50. F of 3, yeah, -150. All right, we want to come up with a 4th degree function, polynomial function that has these zeros but also contains this point. So our first step, let's state the zeros as x equals. So x equals I. Notice that x equals -I is missing, but imaginary zeros occur in pairs. From here, I'm going to build f of x. And then some number we'll find later using this additional information. Remember, you need 4 parentheses because you have 4 zeros. So think about adding 2 over here to the x side. So this 0 comes from this factor. Think about subtracting 2 to the x side, subtracting I, and then finally adding I. Okay, bring the f of x down. Now let's make some wise choices in multiplying because we've got to multiply these 4 parentheses together. I'm going to multiply these 2 and these 2 because these are 2 sets of conjugate pairs. So multiplying these 2 together, it's going to give x squared minus 4. Multiplying these 2 binomials together is going to give x squared minus I squared. Let's clean this I squared up. I know it's tempting not to bring all this other stuff down, but it really is important. All right, so here we have x squared. Remember, this is -1. So minus -1 is +1. All right, let's continue by multiplying these 2 binomials that are not conjugates, so we do have to FOIL. Make sure and put parentheses here. So x squared times x squared is x to the 4th. There it is, our 4th degree function. Plus x squared minus 4x squared, and then minus 4. All right, it looks like I have a little cleanup to do inside that parenthesis. So x to the 4th. This would be minus 3x squared and minus 4. Almost done. How do we find a sub n? Oh yeah, that's right. There was some more given information to help us. So remember, this is x and this is y. So if y is -150, it goes here. A sub n, 3 to the 4th minus 3 times 3 squared minus 4. Um, 81 minus 27. 81 minus 31, 50. All of this would be 50. So times 50. So that's good because let's divide that 50 out and that'll make this a nice number over here. If this isn't a nice number, they're meant to be nice numbers, then we probably made a mistake somewhere. Oh gosh. So that's -3. So, but remember, we're not done until we go back up here to this line and we replace -3 in for a sub n and then finally or sorry, how about this line? This is better. We cleaned it up here. This is the one. So f of x equals, and then -3 So f of x equals, let's distribute the -3 in, -3x to the 4th plus 9x squared, and then plus 12. So there it is, our 4th degree polynomial function, and all the coefficients are real numbers. Again, like I said, I mean, if time's an issue, and this is one of the problems, this might be the one I just let go.